Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The title for today's webinar is Nonlinear FEA of Steel Connections in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer. We are located in Philadelphia, Pennsylvania. My colleague Wieland Gotzer will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I will certainly send you a follow-up email afterwards. So as far as the webinar content for the next hour today, I want to go through several steel connections within RFEM. These would include member, plate, and solid elements. So these are 1D, 2D, and 3D elements within our finite element analysis program. Then we will apply some nonlinear applications such as contact, solids, and surface releases. I want to go through some various recommendations for these types of models such as FE mesh settings, FE mesh refinements. We'll get into contact solids and some of the recommendations and requirements for modeling with those. And lastly, for those of you who are not familiar with our software, we do work with the add-on module system. Those add-on modules are required for design. So RFEM is the main program. You can model, load, and analyze almost any material. But the minute that you want design per a specific standard, such as the AISC, the CSA, that would require those add-on modules. The webinar today will be entirely done within RFEM. So some of our customers who joined us today only have RFEM maybe and no add-on modules. Everything that you're seeing today can be done in RFEM alone. Now the small exception to that is our very last example today. I will touch on our add-on module RF, MAT, and L. This will simply release the nonlinear material properties and allow us to do something more like a plastic design and analysis. With that said, we can jump into RFEM. So to begin with, we want to start off with a beam splice connection. And so I'm going to title this model Beam Splice 10. The type of model is 3D, and we can generate load combinations automatically here according to a specific standard. We're not so concerned with the load combinations and design today, so I'm just going to manually create a load case, and we'll just kind of keep that pretty simplified. Once we click OK, then we can launch our new file, and up pops in the center here our graphic drawing or a graphic dialog box here. We also have our tables to work with down at the bottom. What's nice about this is that you can import and export directly to and from Microsoft Excel if you prefer to work with Excel spreadsheets. We do have our tools to work with up here at the top. We will certainly be utilizing those today. And over on the left-hand side, we have our project navigator, which I think is a little bit more unique to our program. For example, the data tab, which we're currently looking at, this will provide us with all of our input data. You can see our long list of add-on modules is listed here as well, which we won't be getting into today. The display tab is going to control everything that we're viewing graphically within this window over here. This includes our results as well. So typically if you want to turn on or off something, or maybe you'd like to change the color when you're looking at the results or how it's viewed, everything will be done within this display tab. Our views tab is where we can create user-defined views. And as we begin to generate this model, we'll also have some views that are generated by the program automatically as well. And finally, once we run an analysis, we will have a results tab available here. So to begin with, we want to start off with a typical beam member for the first part of our splice connection. So I'm going to draw in a new member, and I will open up my cross-section database here. We have our rolled cross-sections. Once I launch this, I will just see my AISC shapes listed here. I'm going to scroll down to utilize a W12 by 35. Now, steel A992 is one of the default materials within the program whenever we first create a new model, so we will just stick with this for now. and simply clicking on 2 points, one at 0, 0, 0, the other one at 0, 3, 0, we've created just a short beam segment here. Now, when I turn this into wireframe view, the thing to note is that members are 1D elements. So when we're taking a look at the wireframe view, it's just simply modeled by the center line. If we turn this back into a rendered view, of course, all of these cross-sectional properties will be taken into account for the analysis and design. But if we're interested in something like the stresses on the flange versus the stresses on the web, you really can't view those different stresses on different components of the beam because it is being modeled by this simple center line here. Now, what we can do though is to right click on this member and we can utilize this option, generate surfaces from member. So what I've done here is I've converted that 1D member element into 2D surface element. So we have a surface element now for our upper flange. We have a surface element for our web and even the lower flange. When I double click on the web here, you'll notice that steel A992 is still populated, and even the thicknesses are taken directly from that W12 by 35. So this is a very useful feature when we want to generate surface elements from those 1D member elements. Now, the next thing to focus on would be our plate that maybe we're welding this W shape directly to. So I'm going to change around my drawing grid here, and we will snap to the front of the beam to change our origin, and we'll also change the plane here. Now, when I look at my drawing grid, the snap points are set at every foot. That's just default. So down at the bottom of the screen, when I right-click on grid to edit it, you'll notice here that those grid point spacings are set at every 1 foot, as I just mentioned. We can open up our units options and automatically change this to inches instead. So now you can see that instead of 1 foot, I'm seeing 12 inches, and let's decrease this to every 1 inch. I click OK. So now you can see my drawing grid is much more useful when we're working on a much smaller scale, such as a connection. I'm going to orient the model here. So now we're looking at our W shape within the page, and we want to draw our plate element. I'm going to utilize this option, a new rectangular surface. So when I click this option, again, this is a surface element, just like what we saw when we converted our 1D element into our 2D surface elements. I want to create a new material here, and using my filters over on the left, I can filter to metal, to steel, to the ASTM, and you can see here we have our long list of ASTM materials. Now I can also utilize a favorites group. Favorites group is just where maybe I place a few of these materials, for example, what I'm using in today's webinar, that I can quickly have access to without having to sift through that long list. So steel A36 will be the material we select here, which the material properties are populated down here at the bottom so that we can view those. The thickness, we'll set this as 0.25 inches. I click OK. So all I'm doing is just snapping from one corner to the other. And I turn this into an isolated view, just a surface element. So the next thing that we would like to do is to place those openings for bolts. Up next to these surfaces, we also have the option for openings within surfaces. And you can see here we don't have just typical shapes like a rectangle, but we also have circles, parallelograms. You can even draw in your own polygon. So this is very efficient when you have some type of odd opening within a surface connection. It's really no problem to model that. For us, we will stick with a circular element though. So we just simply snap to the center line of that opening. And we can either snap to the radius of where we'd like to place that opening or type in 0.28 inches and click enter. So now that opening was automatically created within that plate element. So I'd like to do the same thing at the bottom here, and I just snap to the center point, type in 0.28 inches, and I have the two openings on the left-hand side. Now, zooming in here to this opening, realistically, we're going to draw a plate right next to this one with an additional beam. This is a beam splice. And in order to hold the plates together, I want to draw some bolt members that are going to hold together those plates when they're in tension. Now, those bolt members we'll get into in just a minute, but what they're going to do is to frame into right in the center of these openings. Now, they're 1D member elements, so the question is, how do we connect those 1D member bolts right here in the center to the rest of our plate surface? Well, the answer to that would be small little rigid links. So what I can do is to right-click on this line, and I can create a node on the line and intermediate nodes. Maybe I select 3 here, I click OK. So now I have 4 nodes located along the line of this opening. I go to draw in a new beam member, and this time the member type will be rigid. So you'll notice that the cross section is automatically grayed out. That's because for a rigid link, the stiffness is set to an infinitely high number, a very, very high number. So the cross section is really irrelevant here. It's really treated as a coupling member. But what we can do is adjust the member hinges. So when I create a new member hinge, you'll notice I have my 6 degrees of freedom, translation and rotation, but we also have partial fixity. So if we don't have a complete release or fixity of one of these 6 degrees of freedom, we can put in here a spring constant. And lastly, if you would like to get into nonlinearities for any of our 1D member elements, you can do so. So if we didn't have a full transfer of a moment, but maybe we had only moment transfer up until a certain value, well, you can set all of that with these options here. For our case, we will leave this as fully fixed. Now, something else to point out is that we have quite a few other members down here called couplings. You'll notice that we have coupling rigid rigid, coupling rigid hinge. Well, when I select one of these, my member hinges are now grayed out. And that's just because these are some quick access tools to get to a rigid link with those member ends already defined. So for example, a hinge would automatically release the moment at either side. So same process, just a little bit quicker so that we don't manually have to define these member ends. Now, a rigid type with the member hinge set as none means that it's fully fixed, and we can simply snap to the center line of this opening to those 4 nodes that I created. Now, in reality, you would maybe want to create several more rigid links here, but for example today, just keeping it simplified, 4 will be plenty. So what we can do is to highlight those 4 rigid links, hold down our control button, and simply snap to our bottom opening to create the rigid links within the bottom there. So now that we're done with the 2 openings on the left, I can turn this into wireframe, select both of those openings, and once again, just making a quick copy, I hold down my control button and utilize the drag and drop feature to make the other 2 holes on the other side. And turning this back into wireframe or rendered view, we can see those openings there. Okay, so moving on, we currently have our 1D plate or 2D plate element drawn here. What we'd like to do is to convert this into a contact solid. So the first thing that I would like to do is to right-click on this member, and we have this option to extrude the 2D surface into a 3D solid. So here I can type in the height of the solid. Now this is important. If I have a 0.25 inch thick plate on the left-hand side and a 0.25 inch thick plate on the right-hand side, the height of my solid needs to be the sum of those 2 thicknesses. So in our case, this would be 0.5. Now in turn, if you had a 1/4 inch thick plate and a 1/2 inch thick plate, well then that would be 0.75. So you just want to add those 2 together to come up with the total height when we're looking at something like a contact solid. The other thing to notice is that we do have the surface type selected here where the extruded surfaces will be set to null. So once I hit apply, let's take a look at what the program has done here. It's created a solid element, so now we have a 3D element rather than a 2D element. We can see that those openings were carried through. That's all great. But when I'm looking at my surface elements, the solid is comprised of surface elements on every end. And that plate that we just defined, if I double click on it, it was automatically set to null. So that's what that checkbox did when we extruded this into a solid. So we want to change this back to standard, and we've already defined steel A36 within the model. The thickness is remembered at 0.25, so I click OK. Now the exact same process needs to be done on the back side of this solid. So selecting my back surface element here, we're going to change the stiffness to standard. Steel A36, 0.25, that's great. But you'll notice that at the top, these narrow sides, I still have my surface elements here defined as null. So around these smaller edges, we're going to keep all of those with 0 stiffness. So we currently take a look at this solid, and it's indicated, if we turn this into wireframe, it's probably a little bit easier to see by this purple node right here in the middle. We can double click on it, and you'll see here the solid type is set to material. So this just means it's a typical 3D element within our finite element software. What we would like to change this to is a contact solid. So we just utilize this drop-down box, and now we have a contact tab here. So I want to jump back to the PowerPoint to discuss a few recommendations and requirements for contact solids. The first being that a contact solid must be a simple surface with 4 boundary lines. So with this picture shown here, you'll notice that here is my first contact solid, but on the longer edges, I have line 2 and line 3 for the top surface and line 6 and line 5 for the bottom surface. If I tried to solve this within RFEM, I would get an error saying side surfaces 4 do not have 4 boundary curves. And that's simply because we need to make some adjustments. We either need to convert lines 2 and 3 into one continuous line, or we can split this contact solid into 2 adjacent contact solids. Either way, it's still going to act like one continuous contact solid, or if we just simply want to combine those lines. So you have to have 4 and only 4 boundary lines to define a contact solid. The next requirement is the top and bottom contact surfaces must have the same integrated objects. So again, we're looking here at a picture of a contact solid. At the top surface, surface A, we have some lines and nodes drawn on there. Now, if I do not make a copy of those lines and nodes and put them on my bottom surface, and I go to run my analysis, the program will say, wait a second, numbers of integrated objects and contact surfaces do not correspond. And that's simply because I need to make a complete copy of these lines and nodes onto my bottom side of my surface. Now, this plays absolutely no influence in terms of the stiffness of our contact solid or anything of the sort. Lines and nodes are just simply meant to be used as modeling tools for surfaces and solid elements and even members. What the program is doing internally is creating FE mesh elements in between those integrated objects. So to be clear to the program, we do need to have those same integrated objects on the top and the bottom. So going back to RFEM then, what does this mean for us? Well, if we take a look back into the model, you'll notice that we have these line elements here, which are shown from framing our surface elements from our W shape. Maybe I want to take a look at here of just the plate elements, and we'll make a visibility here just based on these selected objects. So what I need to do is I actually need to copy these same exact elements to the back side of my surface. So I can do so by selecting them here, by highlighting, and I can hold down my control key. I even need to make a copy of that center node right there. So taking all of these elements, then I can rotate this around, use my Move Copy tool, and I can make one copy in the global Y direction of 0.5 inches, and I click OK. So now you can see those lines and nodes are identical on each surface. So this plays no part in the fact that these surface elements are out here for my beam, but if we didn't have a completely symmetric connection here, this is what you would need to do, otherwise you will get an error. Now in contrast, we actually are going to make a copy of this beam on the left-hand side to the right-hand side. So what we can do with this is to select all of these elements here, and we can utilize our mirror tool. Our mirror tool is exactly like what you would see in AutoCAD, for example. We'll create one copy. We want to mirror it about the global XZ axis, and then we can graphically choose a point here in the center of our plate to mirror that. We click OK. And now you can see that those lines and nodes and everything were automatically generated when we mirrored our entire beam section to the other side. A couple other things to note here, if we zoom in, it looks like our rigid links were not copied over when we extruded this into a surface. Well, that's no problem. All that we need to do is to highlight those, hold down our control key, and to snap to the other side. We'll do so with our opening on the right-hand side. And lastly, for the bottom, you can even select both of these rigid links on the left-hand side, hold down my control key, select on the right-hand side, and then drag and drop to do both holes at once. So we had those rigid links drawn, but we've done nothing yet to model our bolts. And this is where we're going to go back into our member database, and we will select a typical beam type member for our bolts. I want to create a new cross section by going into my cross section library, and under my thin walled sections, I have the option for a round bar. So with a round bar, all I want to do is define a diameter of 0.5 inches. So this is representative of my bolt diameter. I do want to create a new material. So with this, utilizing my favorites group again, I have added steel A325 to my material database. So this was a user-defined material where I've adjusted my properties to match steel A325 directly from the AISC or the ASTM. I click OK. I click OK again. Now the member hinge, I'm going to leave these as fully fixed. I'm going to assume that the bolts and the nuts are tightened as such that I'm going to get some moment transfer between those bolts holding those two plates together. And I click OK. Now with this, all I need to do is just to snap to the center points here between my rigid links. So now hopefully it's a little bit more clear of why we created those rigid links in the first place in order to tie these bolts back into our surface elements. Once I'm done with this, I can right click to exit that dialog box, and let's take a look at the rendered view. So now with our openings, those are still shown here, but the rendered view of our bolts show that circular short member in there to represent the bolt members. Okay, so now that we've pretty much modeled all of the geometry, the next thing that we want to do is to discuss the behavior of our contact solid. So double clicking here back to our solid, remember that under general we specified the solid type as contact, so now we have a contact tab available here. The program automatically determined what surface A and surface B should be. These are our 1/4 inch thick A36 plates. Sometimes you may have to come in here and manually define this just depending on the modeling steps that you take, but most of the time the program is smart enough to recognize what surface A and what surface B. Now, the next two entries are going to define the behavior between these two surfaces. The first is the contact perpendicular to the surfaces. And for this, we have three options. The first is full force transmission. So this is where all of our normal forces and stresses are going to be fully transmission between surface A and surface B. The second option is failure under compression. So if there are any compressive forces or stresses experienced between those two surfaces, then the contact between the two surfaces will fail and we'll no longer have any transmission of those normal stresses and forces. Failure under tension is what we'll be utilizing today, and I think this makes the most sense for our scenario. If these two plates are in tension, then we certainly want the contact between the both of them to fail, and instead we'd like our bolts to maybe kick in with those tension forces. Moving on to contact parallel to surfaces. So this has to do with our shear forces. And for this, you'll notice that we have quite a few more options here. So I'm going to jump back to the PowerPoint and we'll move on to the next slide where I want to explain these 7 options in a little bit more detail. Now this comes directly from our help file and it's the contact options parallel to surfaces. The first option is failure of contact perpendicular to our surfaces failed. So we just set the option for the perpendicular behavior that it would fail in tension. So the option parallel to surfaces then would also fail whenever we have tension within our plate. So it's just a relationship between those two behaviors. Full force transmission, this means that all shear forces will be transmitted. This is despite whatever is going on normal to our surfaces. We'll always have full transfer of those shear forces. Rigid friction is what we'll be utilizing today. This is where we will be given the option to enter in a friction coefficient factor mu. So as we know with shear forces, they can sometimes be dependent on our normal forces times our friction factor mu. So that's what we'll be utilizing today. Oops, sorry. The fourth option, rigid friction with a limit, same type of concept. However, we're no longer given the option for a friction coefficient factor, but rather a tau max. So what this is saying is that we will have full force transmission between the two surfaces up until a certain value, tau max. At that point, then we'll lose that contact and you won't see the increase of any more of those shear forces or stresses. Elastic friction. So this allows us to input two different entries. The first is the spring stiffness coefficient, C. The second is the friction factor, mu. What this will allow you to do is to somewhat define partial fixity then between these two surfaces sliding up and down from each other with that spring stiffness coefficient. So as our deformation increases, that's related to that spring stiffness coefficient factor. But what will also be taken into account is any normal forces times that friction coefficient factor will have influence on our shear forces as well. Elastic friction with a limit. Same concept again, we still have that partial fixity defined with the spring stiffness constant C, but we will instead define tau max here instead of a friction coefficient factor. So once we reach that tau max, we will see no more increase within those shear stresses. And finally, elastic solid behavior, so nothing to do with friction or tau max, just purely a spring stiffness coefficient C. And with this, it's just pure partial fixity between those two surface elements. So going back to the model then, when we take a look at our particular model today, we have failure under tension, and as I mentioned, we will choose rigid friction here. And to emulate these two steel plates sliding against one another, we can use something like a friction coefficient of 0.5, and I click OK. So now we have fully defined the behavior between these two plates on the left and right hand side with a contact solid. So a few other considerations, of course, before we're able to run an analysis. The first one is we need to support the model. We have nothing here such as a nodal or line support. So what we can do for this, you can see our support options shown up here in our tools, nodal support, line support, and surface support. If we open up the line support and we create a new definition, this should look familiar. It looks just like what we saw at our member ends. We have our 6 degrees of freedom, translation, and rotation, where we can fully release these or fully fix them. We have spring constants here for partial fixity, and again, we can get into nonlinearities. This also allows us to define things like slotted joints. Maybe we want this beam to slide up until a certain force and then it will be fully fixed. So all of those options are possible with the nonlinearities. Now with today, we are going to stick with a simple hinged application. So I can simply draw a selection box over the left and right hand side of this beam member. The next thing to do would be to load the structure. So with this, I'm going to go up to my new load case. And like I said, we're going to keep this fairly simple for today, only defining one dead load case. I will leave the self-weight activated, so it will automatically be taken into account with this particular load case. I click OK. Now, the next thing we'd like to do is apply a line load across one of these members. Now, intuitively, we would think, okay, well, let's apply a member load. But remember, we don't have any 1D member elements within this model anymore. We've converted everything to surface or solid elements. So line elements for surfaces or solids must utilize this new line load. So with a line load, we simply specify the load direction in the global ZL direction and give it a magnitude of -50 kips per foot. I click OK, and then I can click to the top of that beam member over here on my left. Now, I think it's perfectly acceptable to maybe not have symmetric loading for this particular connection, but to really see when we have unbalanced loading. So I'm just going to apply my load to my left-hand side and leave the right-hand side without any load except for self-weight. The final thing to look at would be our FE mesh. So under Calculate FE mesh settings, the global FE mesh is always set to 12 inches or 1 foot. Now, the program was smart enough that when we converted these 1D member elements into 2D surface elements, we are on a much smaller scale now. So it automatically recognized that 12 inches was entirely too big for this FE mesh for these particular elements. So that's why it applied these little symbols over here. These symbols just mean FE mesh refinement. And if I take a look by editing what the program automatically put in here, you can place FE mesh refinements about a particular node, a line, a surface, or a solid. Now we're applying this directly to the surface here, and the program automatically decided that 1 inch would be much more reasonable than 12 inches. So if we take a look by going to Calculate Generate FE Mesh, we can see that the program automatically created the FE mesh even at our plate elements where it's required to be much smaller than 1 inch. Everything is done automatically. It's tied to the nodes, the lines, the members. Everything is done for us. But what I do want to show you is that our FE mesh refinements are listed here under our Data tab in our Project Navigator. So if I were to take that FE mesh refinement that I just showed you and completely delete it by just hitting the delete on the keyboard, and let's say that we didn't know any better, but just to leave the FE mesh setting set at this global mesh. So it's currently set to 12 inches. Choosing this option here to regenerate the FE mesh, once I click OK, we can take a look, and I think that we should all be in agreement that this is a terrible FE mesh. This simply will not provide you with your correct results because the FE mesh is entirely too big. Now the program does a little bit of a better job within the contact solid, just because we have elements that are much closer than 12 inches that it needs to tie it together to, but out here you can see that it's entirely too big. So rather what we can do is under Calculate FE Mesh Settings, we can change the global FE Mesh settings to something more like 1 inch. I click OK, the FE Mesh is generated and everything looks much cleaner. Now there is an iterative process with this. You can continue decreasing your FE mesh size smaller and smaller and smaller, and sure, your results are only going to be more accurate. But at some certain time, you're going to be increasing your solution time to be very high in comparison to how much your results are actually changing. So get a better feel for this as you begin to model in finite element software more and more. The other thing I wanted to point out quickly is just another FE mesh refinement. So if we're zooming in here to one of our openings and we determine, okay, we'd like to have a little bit of a finer mesh than what's shown here, we can always right click on any one of these elements, and here is where you'll see the option for FE mesh refinement. We can choose new. We want to create a new definition type, and now you can see my FE mesh refinement is shown for lines. So maybe my target FE length would be something like 0.1 inches, and I'd like to have 4 layers, and it will transition back into the global 1 inch setting. I click OK, I click OK. Now the FE mesh was cleared, and I can see my FE mesh refinement symbol, which is noted by these nodes across my line. Going to Calculate, Generate FE Mesh, then we can see here we have a much finer mesh on the right-hand side than maybe what we're seeing over here on the left-hand side. So just some different options in terms of FE mesh refinements to really focus in on a particular area within the model rather than changing our global settings to something much too small, which really increases our solution time. Okay, with that said, I think we are finally ready to run our analysis. So what the program is going to do now is to cycle through this load case. So we've only applied just this dead load. Now, a couple other things to keep in mind here. This is a nonlinear analysis. So what the program is going to do internally is create these FE elements. And actually, it's taking quite a bit of a long time. It's usually not this long. And keep in mind too, we can see down here what the program's doing. It said verifying authorization, so it was checking my license. It is a nonlinear analysis program, so the contact solid is something that's going to increase our solution time as well, and that's just because of that different behavior that we defined between the two plates. So that analysis is ran, and we are automatically brought into our results tab here, which is available within our project navigator that I mentioned at the beginning of the webinar. So to me, I think the most important thing to automatically take a look at is deflections. Deflections are really going to show us if we've correctly defined our contact solids, maybe our FE mesh, and if it looks to about what we would approximate. So it's kind of a little bit difficult here to see our deformations and what's going on. So under our display tab, like I mentioned before, we have this whole results tree. And under deformation, I can actually choose this option to outline my deformed surfaces. So now it's a little bit more clear on what's going on with our beam elements, our plate elements, even our openings are shown. The other thing to take note of is that under our solids tree, we have a feature here called remove contact solids from display. So when I activate this, my contact solid is no longer shown, and I can see truly what the behavior is between those two plate elements. And just as we defined, when we have tension, it looks like the contact between those two surfaces is failing. But as we move up the length of those plates where we have compression, those two plates are acting together. You can even see our bolt elements indicated by this lines here. They're pretty much keeping the plates together in terms of those tension forces. What we're also probably interested in under the results are our surfaces, and we can view internal forces here such as our contour lines, but maybe we'd like to take a look at our stresses. So when we take a look at von Mises stresses, and there's a whole lot of blue going on here, what I'm going to do is I'm going to make a selection of just my plate element here, visibility by selected objects. And the first thing I want to take note of when we're looking at stresses, especially on a small scale like that, is to jump back to our display tab. And we actually want to change one of the settings here. So under surfaces is the distribution of internal forces and stresses. I'm going to change this to constant on elements. So now when I zoom in, each FE element has its own average value. What was happening before is the program was trying to use a smoothing algorithm to tie all of these together, and you're going to get maybe less than accurate results in terms of our color panel here. The results are still accurate, but just how it's presented to you is much different than averaging it out over each FE element. We certainly have some very high stresses here, 370 KSI. I would attribute most of these to singularity issues. So again, maybe we would want to add in some more rigid links. There's ways to smooth out these singularity issues. But if we're more so interested in the results without these very, very high stresses at these single FE elements, what I can do is to double click on my color panel here. And maybe I change my upper limit to something more like 50 KSI. I can choose the fill button. Then I click OK, and now I'm seeing my results that are maybe a little bit more useful on what's going on with my plate elements. So we certainly still have very high stresses. 50 KSI is over the yield strength of our steel A36 KSI plate. So maybe this is where we size up our plate. Maybe this is where we move on to a plastic analysis with nonlinear materials. I did a full webinar devoted to a connection such as this, but I really went into detail on a plastic analysis as well. That's called Advanced Steel Design and per AISC, and that's on our YouTube channel if you want more information on that. But that's just something to keep in mind in terms of these high stresses that maybe we're seeing. The other interesting thing under our results is to turn off our surfaces, but instead let's take a look at our members. So remember, we define these little bolt elements as members here. So we're able to see these tension forces, which we have much higher tension at the bottom of our connection here, opposed to the top. We can also take a look at shear forces, and we can zoom in here, and if we right click on any one of these members, we we can take a look at the results diagram to get a little bit more information in terms of the magnitude along the length of these small little bolt elements. So again, if we're designing this connection and we want to see the forces on the bolts, that's all possible as well. So that really sums up the first example here in terms of a contact solid. Now, this was a completely symmetric design, which was very nice, but we all know that this typically is not the case. So what do we do when we don't have complete symmetry when we're looking at something like a contact solid? For this, I want to jump into my saved model here, and it's just a typical beam framing into a column. Now, I went about it the same way of converting 1D member elements from my beam and my column. I even went about it the same way for my contact solid for my plate element, but there's something that's slightly different here. Again, we don't have symmetry on the left and right-hand side of this plate anymore. So making a visibility view here based on my plate only, and maybe I turn this into wireframe, and we'll change around the viewpoint here. Here is my plate looking into the page of my beam. You'll notice that I have 4 contact solids defined at the top, 4 in the middle, and 4 at the bottom. And the reason for this is just simply because I didn't have so much symmetry like we did our last model, that I had to create these smaller contact solids in order to meet the requirements. The requirements being that each contact solid must be comprised of 4 different lines, as well as contact solids must have identical integrated objects on the surface A and surface B. But if I take a look at all these contact solids defined side by side, so you notice both of these are highlighted at the same time, we can set our behavior for them all at the same time. So again, I have failure under tension, perpendicular surfaces, and I have rigid friction defined for my behavior parallel to surfaces. So this is going to act like one continuous contact solid. Point being that when you have anything more complex, is to split it up into several more simpler contact solids. So now when we take a look maybe at our results here, let me cancel out our visibility and turn on our results. I am immediately presented with my deflected shape here. So we place this line load, and I turn this into an elevation view, zoom in, and it's doing exactly what I would expect, where I have tension on this plate. It's pulling away from the column. As we move along the plate, places where there are compression forces, well, that's where we should see the full interaction between the 2 surface elements, or actually we have multiple surface elements for these contact solids now. Here are my bolts in tension, of course, as well. So same exact concept. The only thing that I did was split that contact solid into several simpler elements. Now, we often get asked too, how do we take a look at weld connections? You know, maybe you're interested in some type of odd connection, or maybe just strange forces being introduced into a connection. Well, we can also do that with finite element modeling as well. So jumping into another saved model here. This would be completely independent of contact solids. So I didn't utilize any contact solids within this model, but let me explain what's going on. So of course, we have our W shape consisting of our typical surface elements that we've been through many times now. But you'll notice up here is my plate that my beam member is being framed into. Well, when I take a look at this plate element, I no longer change this to a contact surface or contact solid. It's just a typical 3D solid with a material set within the depth of steel A36. So this is just a 3D element within our program RFEM. Now, all of those requirements for boundary lines, same integrated objects, those go out the window for a typical solid element. That's not required for typical solids, just only for contact solids. So you'll notice we have, many different lines and elements framing into the front side of the surface A, but we don't have it shown on the back side. So how about the welds? Well, I created a user-defined view here, and I can turn this on, of my weld solid. So zooming in here, you can actually see the triangular shape of this fillet weld, for example. Now, this weld is just another solid element. I double click on it. The solid type is set to material, just like what we saw with our plate, except for I changed the material. I added in E70 filler metal to represent, a higher strength metal for the weld here. So when we're looking at these solid elements for our weld, we have welds at the top of the flange, the bottom of the flange, and along the length of the web as well. So the other thing to note, if we cancel this visibility, is that we have our 2D surface elements for our beam framing into there. But in order to accurately get our results for the stresses within this weld, you'll notice that I also converted the flange, the web, and the lower flange all to solid elements for this beam as well. So again, a solid type material, steel AID 992. Now, I didn't have to create a solid element for the entire length of the beam, just purely at this connection where I'm interested in my stresses. And that's because we have this solid weld. It must frame into the solid plate, which also must frame into the solid flange and web. So now when we've loaded the structure and we run a simple analysis, we'll get our results. Now again, we can view our surfaces. For example, our von Mises stresses might be of interest to us, maybe not so much out here. But now, unlike contact solids, we also have these solids results available here. So before with contact solids, there was no way to view stresses because there really was no material for a contact solid. But now we just have a typical 3D element. So what I can do is to go back to this view of my weld element, zoom in here, and currently I'm looking at my von Mises stresses, and I can see points where maybe I have a really high stress. For example, this looks like an area where maybe I want to reconsider this connection. Maybe I want to refine my FE mesh a little bit more. You can do so within this solid element for these welds as well. But the point being that you can model the welds as typical solid elements, and then we can view all of these stresses within here as well, including strains and plastic strains if you wanted to get into that with nonlinear materials. So we can also take a look at our plate element. So let me cancel out of this visibility mode. Maybe we select, let's see, turn this into, select just our solid, create a visibility by selected objects, view our results again. Again, this is just von Mises stresses, and we can see the points of high stresses here, right where that weld is framing into the top of the flange and bottom flange. So just another approach for a welded connection, independent again of contact solids. Okay, so moving on to our last example. I'm going to open up another model here, and this would be a simple tie rod type model. Again, we're on a very small scale here. And just for the sake of time, of course, I didn't have time to model all this, but I want to point out a few features of what's going on. So over on the right-hand side, we have a fully fixed nodal support over here. Now, for the most part, the rest of these elements are solid elements. So for example, if we take a look at the front part of our tie rod, I can double click on this. Just like what we saw before, we have the solid type set to material, steel A36. So again, those conditions of 4 boundary lines comprising a contact solid do not apply to typical 3D solid elements. You really can have any shape that you would like for solid and surface elements. Now, the bolt passing through the ring of this tie rod is also modeled with solid elements. And we even have our ring here defined by an additional solid element. So what we're trying to emulate here is this bolt passing through the tie rod ring. We have a load placed on here on either side to represent tension within that bolt. We want to look at our FE mesh refinements here. So we can see here under calculate, FE mesh settings. The global mesh settings are set to 0.03. This is about 0.36 inches. So something very, very small for this type of model. You'll notice this cube within the center here. Well, this is once again another FE mesh refinement. So just like what I pointed out before, we can even apply FE mesh refinements to solids. I set something just slightly smaller at 0.02 feet. And then the program will automatically generate this FE mesh, tie everything together so that we manually don't have to worry about any of that. Okay, so now that we have discussed what type of elements are going on here with this tie rod, let me turn this back into a rendered view. We want to run our analysis. Now, in reality, when we run our analysis, we should take a look again at the deformations. That's kind of always my advice on viewing if we're seeing our expected behavior. So with this bolt element passing through the eye, and we turn this into elevation view and maybe into wireframe, we can see here that it looks like the bolt is fully fused to the front portion of this ring element. This is not really what's going to happen. In reality, what we would hope to happen is that this bolt would release away from the ring element where we have tension forces, but in the back, we would still have full fixity here where we have compression where the bolt's bearing onto the ring. So how do we exactly take that into account? Well, let me turn off the results here and going back into a rendered view. I'm going to turn off my FE mesh under my display tab. We can scroll down here just to quickly turn that off with a checkbox. So here is all of my input data. Now, as I mentioned before, every solid element is composed of surface elements on the exterior. So again, here's a surface element. We can view all of these surfaces available in our data project navigator. All of them are set to null, which means they have no stiffness. They're not playing any importance in terms of the analysis of the program. They're just kind of boundary surfaces for our solid element. But as I scroll through these, I'll notice surface number 3. Surface 3 is the shared surface between the bolt element and the ring element. So this is where we need to have some influence here on the connection between those two solid elements. So let me create a visibility by the selected objects. I'm going to scroll in here and I'm going to right click under the surface to turn on the local axis system. So looking at the local axes of this surface, you'll notice here that I have my local X and Y coordinates. So that's translation. Here we see left to right, front to back, but then I have my Z coordinate. So just keep that in mind that that's normal to the face of this surface. Over in the project navigator again, if I scroll down just slightly, I will see surface releases. And this is where I want to right click and create a new surface release. So here the program initially asked me which surface would I like to apply this to. So I can graphically choose surface number 3. I could type it in. I could even choose from my drop-down box here. I need to define the surface release type by choosing my option over here on the right, and up pops an additional dialog box. So now you'll see my 3 degrees of freedom, translation in the X, Y, and Z. So what I'm going to do is I'm going to activate all 3 of these. So this is my surface release type. So in the local X and local Y directions, I'm actually going to apply a small partial fixity. And that's because we're going to have some resistance of this bolt sliding left and right, front and back. So we'll do the same thing for lowercase y axis. Then we have our local z axis here. And again, sorry, I forgot to reiterate that these are lowercase x, y, and z, not to be confused with global x, y, and z indicated by a capital X, Y, and Z. So here for the translation direction in the Z component for this surface, I want to set one of these nonlinearities. And the option that I'm going to choose here is fixed if positive PZ. So when I have any forces that are in the positive direction of this surface, I want there to be full fixity between whatever objects I will soon select, which we'll see that in just a minute. But whenever I have tension forces in between, maybe my bolt and my ring element, I want that release to kick in and will no longer have transmission of any forces in that direction. I click OK. So what is happening here with a surface release? Well, this picture indicates what's going on. So this pink surface is actually my surface number 3 here. And the program will internally create an additional surface to apply that generated release surface. So it's something internally that's going on within the program. Now, what we do need to define is a released object. So we have defined the release type, but what exactly do we want to release? Well, this is where I'm going to choose my solid elements. We can exit out of this visibility mode, and here I'm going to choose my solid on the left-hand side, which is the left-hand portion of my bolt, as well as the right-hand portion of my bolt. Now, there's also a solid within here too, but you can't easily select it graphically, and that's only because we have an additional solid defined for our ring element. So what I can do is click OK. I only have solids 5 and 7 defined here. I click OK. And first of all, I'm going to zoom in here, right click to turn off my local axis system. And just like what we saw with our surface elements, we have all of our solids listed here as well. So what I can do is just to scroll down, and finally I find solid number 4 is the additional solid I would like to release. So what I can do is to choose my surface release from my tree here, or you can see a faint dotted line, which represents that surface release as well. To double click on it, and I can just type in comma 4. I click OK. So now we've applied that surface release, and let's rerun our calculation. So you can see down here our status. The program is creating all of our FE mesh elements. Again, it takes a split second longer. Number one is because we have quite a few FE elements, not only for our surfaces, but we've introduced solids. So throughout the depth of the solid, we have FE elements, but we've also introduced a nonlinearity with that surface release. So the program must determine what's tension and what's compression between the bolt and the eye. So once this is done solving, we will see our results presented to us directly in RFEM again. And it's almost done. Okay, so now we are taking a look at the deflected shape. Again, my recommendation, always jump to that deformation here when our results are presented to us. Let's turn this into a wireframe view, and now we can see much better behavior between that bolt element and the ring of the tension rod. So what we see here is that when we have those tension forces, I actually have a small gap here, but I rotate it to the back and I'll see full compression where that bolt's bearing onto the ring element. It looks like all of those forces are being transmitted. Now that's fine for the deflection, but maybe we want to double check everything with our stresses. So for this, I'll take a look at my solid elements and in turn my von Mises stresses. Now jumping back to my views, I want to activate maybe just my bolt element here. And this is going to confirm that we have pretty high tension stresses up here at the front of the bolt, which makes sense based on the deflected shape and the loads that we have applied. If we rotate this to the back, we have much lower stresses where this bolt is bearing onto the eye of our ring here, where that will help with this overall stiffness. So taking a look at the ring element, same type of concept. When I look up here at the front, I have relatively low stresses, and that's just because I don't have that bolt element bearing on the ring anymore. But at the back side and the top and the bottom, I have much higher stresses where we begin to have contact between those two solid elements. Now, the other thing to notice is that under the bolt, if we just generate this view, maybe we're interested in viewing what our stresses are along the depth and length of this bolt. And with solids, it's sometimes hard to tell, well, okay, I can see externally here what's going on, but what's going on within the inside of this solid element? And that's where we have something called a clipping plane. So under Insert, Clipping Plane, here you'll notice that we're immediately slicing this solid element in half, and we can invert the clipping plane so that we're viewing the other side. And here we can set a certain step, so something pretty small like 0.05. Now as I toggle through these eccentricities, I can actually see what's going on within the depth of the bolt element. I'm probably most interested right here in the center where we have the most activity going on with our stresses. So that's something you can easily utilize for either solid or surface elements if you're interested in kind of knowing a little bit more of what's going on internally within these elements. And one last thing to cover is that you'll notice here that my solid stresses are not exceeding 36 KSI. Well, that would be pretty good luck, but the reason why I did that is because I'm utilizing nonlinear materials within the program. So jumping back to my data tab, let me turn off my results and take a look at the rendered view. And my materials are listed here of what I'm using within the particular model. So the first one is steel A36. So that's the front portion of this model as well as the two end solids for my bolt. When I double click on this, you'll notice the material model is just set to isotropic linear elastic. So any linear elastic material is already included within RFEM. So that's fine for this front portion of the model. Now, okay, there we go. And then as far as the rear portion of the model where I'm most interested in this connection here, I double click on the material. You'll notice that I changed the material model to isotropic nonlinear elastic. So any nonlinear elastic, plastic, and so forth, that is where that add-on module RFMat NL will come into play. So that will release all of these various options to do a nonlinear material analysis. So for example, you can see here in our details, which if this opens up, I don't know why there's a little bit of a lag time. It must be the FE elements, but we can see here the yield strength is set to 36 KSI more or less just from our steel A36 material. So now when we take a look at the model and we ran our analysis, which what we just saw, we can turn back on our results and take a look at maybe our view of just our bolt. Again, nothing is going to be above this 36 KSI. So what's happening is the load is being distributed on these FE elements. The minute that that FE element reaches the yield strength, the load will be distributed to adjacent elements until that is a fully complete process. So that's something that, again, I get a little bit more into with the other recorded webinar on our YouTube channel. So if you are interested in that, you can find that there, or send me an email and I can point you to the right direction. Okay, so that concludes the webinar for today. I know that was quite a bit of information, but keep in mind, almost everything entirely that you saw today is just our main program RFEM without touching any of our add-on modules. You can find more information on our website at dlubal.com, and as I mentioned, we have several other social media sites, including our YouTube channel, where all of these webinars are recorded and put online, but also Facebook and LinkedIn and so forth. Our email for our Philadelphia office is info-us@dlubal.com, and our phone number here is 267-702-2815. Now, many of you are interested in upcoming webinars. We typically put these on our website at dlubal.com under support and learning webinars. As you all know, I send out a reminder email when those are upcoming as well. PDH credit is available for today's webinar. I just ask that you please let me know through email who is in attendance and send that email to info-us@dlubal.com. So again, info-us@dlubal.com. Again, just let me know who is in attendance today, and I'll be happy to generate that certificate in a PDF form and send that back to you. And with that said, I want to thank everyone for attending today. Again, if you have any questions, feel free to reach out to us, and I hope to see you at the next webinar. Thank you.